Today we're very pleased to welcome Professor John Plain. John is a professor of atmospheric chemistry at the University of Leeds, where their expertise focuses on understanding the chemistry of planetary atmospheres through laboratory studies, atmospheric measurements, and modelling. In 2020, John was elected into the highly prestigious position as a Fellow of the Royal Society. In addition, John's numerous accolades include being awarded the EGU Wilhelm Bergnuss Medal in 2017 and the National Science Foundation CEDAR Lecture Prize in 2007. Today, John will be speaking on the role and impacts of cosmic dust in the atmospheres of Earth and Mars. So I'll hand it over to you, John.
That's great. Thanks, Jasmine. Right. Let me start off by saying good morning to everybody, and I'd just like to mention my various collaborators at Leeds, Wu Feng, Dan Marsh, and Caitlin Goff. I'll be showing work from them today. And then international collaborators, Juan Diego Carrillo Sanchez, Francisco, and so on. These guys are involved in the meteoric input function, the modeling of Mars. These three gentlemen here are involved in the Maven mission around Mars, and I'll be showing results from their work. And finally, Diego Hunches, who's the NASA scientist for Maven. So let's start off with a question which might seem very simple, and that is, how large is the cosmic dust flux into the Earth's atmosphere? And when I reviewed this a decade ago, I found that the estimates ranged between 3 and 300 tons per day, which is a factor of 100, not a very satisfactory state of affairs. And so the first part of this talk will show you how we tried to narrow that down, and the result we got is actually pretty close to the geometric mean of those two numbers, interestingly. So what I'm going to do is talk first how we determined that, and then we'll switch. So blue is the Earth, and then we'll go to Mars, use that to calibrate the dust input into Mars, and then construct a global model of magnesium ions in Mars' atmosphere to compare with Maven observations, and then look at 3 ions here in the middle ionosphere of Mars, and finally look at the accretion rate of exogenous carbon. So that's carbon contained in cosmic dust particles that survives entry, reaches the surface, and then can produce methane, which is now very well constrained from various types of measurements. So beginning with the sources of dust, there are really 3 groups. The first of them is the Jupiter family comet, and this is actually the orbit of comet Encke, which we think actually provides most of the dust coming into our atmosphere. So this is a comet that's been captured by the gravitational field of Jupiter, and now is making an orbit of only a few years inside the orbit of Jupiter. We then have the asteroid belt, main asteroid belt between Mars and Jupiter. And so these rocks and so on, which didn't in the end form planets, collide with each other, produce little bits of dust, and these can migrate into the inner solar system. And then there are longer period comets. So this is Halley's Comet, which is well known, and this has got a period of about 76 years. But then there are also comets that come from further afield, the Kuiper belt beyond Jupiter, and even the Oort cloud. So the first question is, which of these is making the major contribution to our atmosphere? Now, if you don't know much about comets and so on, you may say, well, you know, how can a comet be a source of dust? This is a close-up picture of Comet 67P from Rosetta. And here is the co-discoverer of it with a model at ESTEC in Holland. And you'll see that this comet actually is like a lump of coal. It has an albedo very similar to that of coal. And when the comets like this approach the inner solar system, they get heated by the sun. And when the volatiles that are shown down here start to evaporate, they take with them the dust that is embedded in the ice, and that is how comets provide dust in the 1AU. Now, this is a figure of the global iron input into the atmosphere, and I'm going to be using units of tons per day throughout the talk. And these are various ways of estimating it. So this is global modeling. WACCM is a whole atmosphere chemistry climate model that we've used extensively. And that's the amount you need to put in to explain the iron layer in the upper atmosphere, which I'll show you in a minute. This is based on high performance, large aperture radar measurements. There's then an astronomical dust model that would suggest that much iron is coming in. This is an actual measurement of the flux of iron in the upper atmosphere. And again, I'll show you how that's done in a moment. And this big number here is the amount of cosmic iron that is apparently accumulating in polar ice cores. So we've got a factor of 50 here, which is an uncomfortable range. Let's start off with the zodiacal light. So this is a nice picture from the Southern European Observatory. You can see it there. And if you take a cross-section through it there and make a plot of the normalized flux, the black line here against position above or below the plane of the ecliptic, then dust models of how dust is launched from these different sources in the solar system and migrates to the inner solar system would predict that Jupiter family comet dust is the red line, and that's a very close match. The asteroids too narrow because they are the dust source is too close to us. It's just beyond Mars. And these Halley-type comets, including Kuiper Belt and Oort cloud comets, you see is too broad. So just looking at the zodiacal light suggests most of the dust is from Jupiter family comets, and that turns out to be the case. Now, we've, over the years, developed a model of how a dust particle entering the atmosphere will heat up and ablate. So inelastic collisions with air molecules causes the particle to melt at around 1800 Kelvin. The volatile elements, sodium and potassium, evaporate at that point, but that's not enough to keep it cool. So it will carry on heating to around 2000 Kelvin. And then these are the three main elements along with nickel that then evaporate. And finally, if it keeps on going, if it had enough velocity or mass when it entered the atmosphere, it can reach around 2400 Kelvin, at which point the so-called cat elements, calcium, aluminium, and titanium, evaporate. And we have captured all of these processes in our chemical ablation model, which we call CABMOD. And we have tested this against a meteoric ablation simulator in the lab. So I'll just briefly go through this. The center of it is, well, inside this vacuum chamber is a tungsten filament on which we place some micron-sized meteoritic dust particles. We can then flash heat this using programmable heating to mimic the heat that the profile, the temperature profile that the particle would experience during atmospheric entry, and we observe that with a fast response pyrometer. We then have a camera up here to watch what's going on, and we cross just above these particles with two laser beams, which are tuned to look at one of a pair of metals. So I'll show you sodium and nickel in a moment, evaporating from the particles. And that requires a very high repetition laser to capture it in real time. So this is a movie showing the tungsten filament, which will be across here. And what you'll see is the little particles melt, so they as the filament heats up, and then they run along the filament due to a process called electromigration. They don't drop off it, luckily. And so here we go in real time. And there are the three particles running along there. Of course, it gets white hot, and so you can't see it anymore. So these are the results. And what I'll show you here is three different sizes of particles in microns. And we have simulated the temperature profiles shown in red for 3 different entry velocities. Note the time scale is very, very short. We're talking about just a few seconds. Now, if you have a small particle that enters slowly, nothing appears. That bar up there shows the amount of nickel that is ablated. Whereas if you have a big particle and you enter rapidly, you see you get complete ablation of all of the nickel. The orange is showing the sodium laser-induced fluorescence. A number of experiments are superimposed on this, and the brown is iron, and then our CABMOD model are the dashed lines here. So this is just to show you the process that we go through in order to tune up the model. And it's critical that we have confidence in that for the next step. Ablation in our atmosphere produces layers of metal atoms centered roughly around 90 kilometers. Here are measurements at mid-latitudes of 5 different metals. And what's interesting here is if we start off with sodium and potassium, they are more or less in the ratio they are in cosmic dust. Iron should be 16 times bigger than sodium. It clearly isn't. That's because it doesn't ablate as efficiently. And calcium, remember, one of the cat elements, only ablates if you get to the highest temperatures. And this is very depleted. There's a similar amount of calcium as sodium. And on a log scale here, you see the depletion is a factor of 100. So this is really prime evidence for this process of differential ablation. Once the metals ablate, the interesting question in our atmosphere, which everybody knows is strongly oxidizing, is why these atoms occur at all. And the reason is that above 85 kilometers, there are lots of O and H atoms, and these reduce metal compounds back to the atoms. When you move above 100 kilometers, now you are starting to get into the E region of the ionosphere. And these metals, of course, very efficiently charge transfer with the ambient O2 plus and NO plus ions. And so you have metal ions up here. Below 85 kilometers, the metals become oxidized and then polymerize into nanometer sized particles known as meteoric smoke. And you may say, how can I be confident about what I've just said? And the reason is that we have studied all of these reactions shown with solid lines here in the laboratory. So we've measured rate coefficients under mesospheric conditions. These schematic diagrams here, the ionized species are shown in blue, the neutral ones are in green. And this is just showing the chemistries of sodium and iron. Now, these two elements, if they are being ablated in the upper atmosphere, where they occur as ions, there should be a downward flux of them towards the part of the atmosphere below 85 kilometers where they are removed as this meteoric smoke. And if with a LiDAR system, you can measure simultaneously the concentration of sodium at some altitude and the vertical velocity of the atoms, which you can do using a Doppler, the Doppler effect, the time average of the product of these two gives you the flux. And here is a plot of the vertical flux of iron and sodium in the atmosphere. And you'll see it's about 0 up here. But once you have significant ablation, you get large negative value, particularly for iron, because more of it ablates. There's sodium. It's negative by convention. If it were positive, it would be an upward flux. And this gives us, if you then extrapolate globally, 0.3 tons per day of sodium is being injected, and the global iron flux is 2.3 tons per day. If you now go to the South Pole, underneath the base, there is a large water well here, which you see extends down over 100 meters, and all of the ice, fern, and snow that was in that volume has melted. Cosmic dust particles that don't completely ablate, they melt and then re-solidify, form what look like little glass marbles. So these were molten silicate particles. And these obviously collect at the bottom here, and you can vacuum them out, and they're easy to identify. And you can then determine a flux, and that's about 4 tons per day of these cosmic spherules. And our CABMOD model predicts how much of an incoming population of particles will turn into spherules, as opposed to do nothing or ablate into metal atoms. Now, these 3 families of particles here have very different entry velocities, which is plotted here. The asteroids come from just beyond Mars, so their entry velocity into our atmosphere is very strongly peaked to the lowest entry velocity, the reverse of the escape velocity, so it's just over 11 kilometers a second. The Jupiter family comets a bit further afield, so you see their velocity distribution is starting to show a bit more population at higher velocities, but the long period comets, Halley type and so on, are clearly, there's a lot of them enter at very high velocities, and these will tend to ablate and contribute disproportionately to the metal atoms, whereas it's the slow ones here that will tend to form spherules. And we also have an idea of the size distribution of each of these from this zodiacal dust cloud model produced originally by David Nesvorny. And so you can take for each of the populations its velocity distribution, its mass distribution, put that through the CABMOD model and predict the flux. And we have 3 fluxes here. We have iron, we have sodium, and we have cosmic spherules. And the total flux of each of these is equal to the flux from the JFCs, the asteroids, and the long period comets with these 3 coefficients. So we have 3 simultaneous equations: iron, sodium, and cosmic spherules, and the fluxes are produced from the CABMOD model combined with Nesvorny's ZODI model. Well, we have 3 simultaneous equations, 3 unknowns. We can solve them unambiguously. And this is the result. So this is the mass flux from the 3 different sources and the total. And the grand total in red here is 28 tons per day. And that's now been confirmed from other work that I won't go into now, but we can use that. If you just look along this bottom row here, you'll see that around 70% of that total is coming from the Jupiter family comets. But if you look at ablated atoms, you'll see that most of them come from the long period comets because they are entering at high speed. Of that total, around 30% ablates. So, having got that number, we can now take the same CABMOD ZODI model and go to Mars. But sorry, just before we do that, I'll just show you confirmation that we're on the right track here. This is the Concordia base, the French base in Antarctica, and this trench here that they dug out, all of the snow was put through this melter, and then these different spherical types of cosmic dust particle were counted. So that's a classical cosmic spherule. This is a stony spherule. This is called a scoriaceous dust particle. It's partially melted, and that's an unmelted one. And if you look at this plot here, this shows as a function of size the cosmic spherules that were measured at Concordia, the red dots, and that's extended out here using the South Pole water well that I showed you earlier. And the orange squares here are the CABMOD ZODI model. So that's very good agreement. If we go to the unmelted meteorites, we have the blue points, and the CABMOD ZODI model is great up to about 100 microns. Below that, we predict far more. Now, it may be that they're being undercounted, or there may be some other reason, but basically this is a good enough agreement, we feel, to now have confidence in the CABMOD ZODI model. Let's now go to Mars. So Mars, which you can see orbiting around the sun here, has an unusual orbit. First of all, it's very eccentric. So during the southern summer, it's much nearer the sun than in northern summer over here. It also, the orbital plane is inclined to the invariant plane of the ecliptic of the solar system. So, and it crosses that plane at these 2 points over here. So let's go to southern summer. It's very near to the sun, and this creates a lot of heat in the atmosphere, which causes dust storms. So this is the dust storm season. It also is the period when there is the biggest amount of cosmic dust input into the atmosphere and ablation. In contrast, the minimum input is during northern hemisphere summer over here. And this movie shows you, as a function of altitude and latitude, the injection rate of magnesium from ablation. And so we're going to start off in southern hemisphere summer. You'll see that the ablation is occurring much lower over the winter pole here. That's because the whole atmosphere has got very cold. CO2 is plated out onto the surface. And so the altitude at which the incoming particles hit enough CO2 molecules to heat up and ablate is lower. So let's now run this through a Martian year. And we're now coming up to midsummer, and you see there's a peak here. Now, as we move towards the equinox, you see things get a lot more even, and now we're moving towards southern hemisphere summer. There's a lot more dust coming in here. It's up at 90 kilometers. Now we're moving back towards spring. So we're subsiding here as the atmosphere gets very cold, and this is coming up. Right, let's move on to the chemistry. This is another of these schemes. So blue is ions, green is neutrals, and the chemistry is a little bit different in Mars because of all this CO2 and CO. But again, in the lab, we have measured quite a lot of these reactions, and the others we can calculate quite with a reasonable degree of confidence. Basically, you end up with magnesium carbonate, which attracts water, and this forms little, essentially dirty ice particles, which probably give rise to the noctilucent clouds or mesospheric ice clouds that have been observed in the planet's atmosphere. You can take that and now start to do modeling, initially 1D, but more recently we have used the PCM, general circulation model from the Latmos group in Paris. So this is a whole atmosphere model extending from the surface to the exosphere around 200 kilometers, and it includes ion molecule chemistry and various things here. What we have done is put in 47 magnesium neutral and ion molecule reactions that I showed you in that schematic diagram, and that the complete input function or the MIF for magnesium that I showed you the movie of. And then more recently, we've added the chemistry of these 3 elements here. So Maven, which is shown in this diagram, has on board an imaging ultraviolet spectrograph, IUVS, which is able to image air glow above the surface from about 80 kilometers upwards. And just after Maven arrived at the planet was almost hit by comet Siding Spring. So this is an Oort cloud comet. You can see in this oblique view, it's nowhere near the plane of the solar system in its orbit, and it will not be returning. Having narrowly avoided Mars, it was about 138,000 kilometers from the surface. This created an enormous dust trail, which the planet then went through, and the result is shown here. This is what the IUVS spectrometer, so this is in the near ultraviolet, observes under normal conditions. So we have a CO2 Cameron bands, more CO2 and some oxygen here. This is what you would expect in a CO2-rich atmosphere. But immediately after the planet went through the dust cloud, you suddenly see, if I just oscillate those backwards and forwards, a huge peak here of magnesium ions that are glowing in the sunlight. There's a little bit of magnesium and Fe and Fe+. And modeling that, what we showed was around 80 tons of cosmic dust was dumped into one hemisphere of the planet in only 70 minutes. And there would have been up to around 120 visible shooting stars every second. So fantastic light show if you were a Martian. Has that been seen on Earth? Yes. The last great Leonid storm was in the last century, 1833. This is a woodcut of it, and there were thousands of shooting stars every minute. So something rather similar to what Mars would have experienced. What about normal background metal layers? Well, the only layer metal that can be seen routinely by the IUVS is the magnesium ion signal. And this is what is observed. Ignore anything below 80 kilometers. There's too much scattered light down here for this signal to be reliable. But what this shows consistently is the peak in the Mg plus is early in the morning, just after sunrise. It's not in the middle of the day, which is typical of ions in most ionospheres and includes O2+, which is the dominant ion up here in the Martian atmosphere. And the model actually captures this very well over here. And what actually is happening is the tidal effect. The long-lived atomic magnesium ions are brought down by the diurnal tide to this altitude and compressed here at this time of the day, and then they disperse again for the rest of the day. So this is not actually a photochemical signal. And if you compare years in the model, you can see there's some variability, particularly in this year here, Mars year 34. And this is when there was an enormous dust storm that covered the whole planet. This pushes things up, and it has the effect of reducing the amount of Mg+. By the way, it's worth just noting this point here, and that is below about 110 kilometers. Magnesium ions are the dominant ion. It's only higher up that O2+ and NO+ are more important ions. So the ionosphere down here is controlled by these meteoric metal ions. Let's now look at the Mg+ layer. This is at mid-latitudes, 40 degrees north. And so again, we're looking at local time here and altitude at different points on the orbit throughout the year. So this is spring, summer, autumn, then we go into southern summer. And this compares Maven measurements over here. And, given that under normal conditions, the magnesium ion signal is tough to detect against all of the other emissions going on at this part of the atmosphere and scattered sunlight and so on. These are actually really difficult measurements to make, and hence you have to keep in mind there is going to be some noise in them. But what we can see here is that if we go to aphelion, so this is close to northern hemisphere midsummer, the peak of the layer we predict is around 90 kilometers, and that is the case. As I say, ignore stuff below 80 kilometers. So that's good. And you'll notice if we go to southern summer, so this is now perihelion, the magnesium ions have almost disappeared at northern mid-latitudes, both in the model and in the measurements. And the peak of the layer has moved up here to around 110. So again, that's nice to see that at least we're able to capture some details. If you go instead to look at the magnesium ions versus altitude and latitude over a range of solar longitudes, what you can see here is that very often the model is predicting very large amounts of magnesium ions in the polar regions, well below 80 kilometers here. And again, these will be the only positive ion in the plasma down here. Now, unfortunately, Maven, IUVS, doesn't make reliable measurements below 80 kilometers. So this very interesting feature is not being captured. There are hints you see here at high latitudes, and there's a hint here that there is a big concentration of magnesium ions, but no more than that. The other instrument on Maven is the neutral gas ion mass spectrometer, or NGIMS. And this has been very useful because they are able to occasionally operate in a campaign mode where they make what are called deep dips. So this is where the satellite dips down to around 130 kilometers. It can't do this very often because it has to use fuel to restore itself to higher orbit again. And it can only actually do deep dips because it's in a very elliptical orbit. So here are some results. We have magnesium ions and Fe plus in light blue and dark blue, and then the neutral CO2 divided obviously by a very large factor to put it on the same scale. And there are two big surprises that came out of this. The first of these is that both the metal ions have very, very similar scale heights. So they're decreasing more or less with the same slope plotted on a log scale. And that's very surprising because iron is 2.3 times heavier than magnesium, and you would expect it to have a smaller scale height as a result, but it certainly doesn't, except, possibly in that one, but here it's clearly is slightly bigger. And the other really big surprise is that CO2 has the same scale height as the ions. So the neutral and ionized atmosphere seem to have the same scale height. Again, a surprise because the classical idea of ambipolar diffusion would suggest the ions would have twice the neutral scale height. And so what's very weird about this is that if you look at this data, you say, oh, well, the atmosphere is well mixed. That's the only explanation. But because NGIMS can look at other things, other neutral species, it showed that the turbopores, above which you should start to see separation by mass, is down here. So this is one mystery that needs to be explained. How does the PCM model do against Maven? So here are the 4 deep dips that I just showed you. The Maven measurements for each ion are in red, and the model is in blue. And you can see things don't look so great for sodium ions. We don't really understand why that is, because if you look at magnesium ions, although deep dip 1's not great, the others are actually pretty good as capturing the scale height pretty well and the absolute amount. And if you go to Fe plus, there's actually pretty good agreement on all 4 of the deep dips. So why sodium is behaving oddly is very strange. Its mass is almost the same as magnesium, 23 versus 24. So there's a nice mystery for the future. And finally, here again is the deep dip data, which is now plotted. So we have the 2 ions in green and blue, and CO2 once again in pink. And then also shown here is O2 plus. So that's the dominant ion. And on this scale, it's divided here by 50 and down here by a factor of 1,000, the CO2 by 10 to the 10, just to get everything on the same sort of plot. This is what you could say is normal. So you see the ions are all here nicely mixed with the CO2. O2 plus is not, because chemistry dictates it has a short lifetime down here, and so it's increasing in mixing ratio as the CO2 falls. But look at these 3 examples here of what we've termed in this paper from 2017 anomalous layers. Here's this big fat, quite thick layer, which of the 2 ions, not really seen in O2 plus. Here's an example where nothing is seen in O2 plus, but again, these 2 metallic ions are in this big layer enhancement, more than a factor of 10, but it's also over quite a large vertical range. And here's an example where we have one of these layers also seen to some extent in O2 plus. So what's going on here? Got no idea at the moment. There's no relation of these two with the remnant magnetic fields in the southern hemisphere of the planet. They're broader than the sporadic E layers we find in the terrestrial atmosphere, and sometimes seen in O2 plus and sometimes not. That's a nice problem for the future. So I'm going to spend a few minutes now talking about organic material in cosmic dust, because this links to one of the sort of big questions on Mars, and that is methane, which you'll know there's a long history of observations that either showed it was there, wasn't there. There's currently disagreement between the TGO and the tunable diode laser spectrometer on one of the rovers. And let's just see what organic material in carbonaceous chondrites might tell us. So there's free organic matter. We know various compounds like this. These will easily evaporate. We're more interested in the bulk of the organics, which is refractory organic matter, a bit like tar, which might degrade or should degrade at higher temperatures, particularly undergoing a process called pyrolysis, where oxygen inside the particle is available to essentially combust the organic matter into carbon dioxide. And there are various polymeric organic materials like kerogen, which is probably a good model for this tar-like material. And the sort of rule of thumb is that about 5% by weight of carbonaceous chondrites is organic, though it seems it may be much higher, up to 40% in very fresh cometary dust. So it may be degraded over time in the interplanetary medium. And this stuff, the tar-like material, is probably the glue which binds together mineral grains, so that's very important. And of course, if that material fails during atmospheric entry, you could get fragmentation of meteoroids, which would change the picture of differential ablation that I showed you the cartoon of earlier. These are electron micrographs of cosmic dust particles captured in the atmosphere, A and C, and you can see they are these very loosely bound, fluffy agglomerates of smaller grains. And that's a picture from the Midas instrument on Rosetta. So this is a fresh Comet 67P particle, which is showing the same fractal-like conformation. So in the lab at Leeds, we built a new meteoric ablation simulator to look at organic pyrolysis. So what we do is up here in this vacuum chamber, we put some powdered meteorite. This valve can swing open and the particles drop down through this funnel onto a hot plate set at some temperature. And then we measure, using a fast time-resolved mass spectrometer, the evolution of CO2, and we used two different samples, Allende and Gibelet Winselvan, to do this particular study. So this is an example of the is very nice experimental data that we get. The black points here show the fraction of CO2 emitted with time after the particles fall onto the hot plate at this particular temperature, and they're 36 microns in size. Now, this kinetic profile here is not a simple exponential. It actually can be fitted with very nicely with that red line as the sum of two exponential terms, and we're pretty sure that these correspond to fast release of CO2 from what is known as soluble organics found in meteorites, and then there's this insoluble fraction which creates the rise here at later time. So we've put the kinetic information from this into CABMOD, and we can now start to address this question. A study from John Moores and Scherger et al., JGR Planets in 2012 showed that if you irradiate meteoritic fragments with UV light, you actually generate methane. And they estimated that at least 20% of the organic carbon was converted to methane under UV light. Now, the long-standing estimate of organic carbon reaching the surface was 0.66 tons per day from George Flynn a while back now. And this would create over 2 ppb parts per billion of methane in the Martian atmosphere, which is in conflict with the observations from the surface. This is Chris Webster et al. In Science, that a lot of the methane is only 0.7 ppb. If you go to our Kabmod-Zodi model, now with organic carbon included, we show that the amount of exogenous carbon that actually reaches the surface, so in other words, where the particles did not reach a temperature above 700 Kelvin and the organics started to pyrolyze or completely pyrolyzed, the amount of organics reaching the surface is 0.014 tons per day, 40% of which is the soluble, more reactive carbon. And that's assuming this 5% of these particles is organic carbon. So this is obviously a big decrease from the old Flynn number, and that partially reflects the fact we have a more accurate estimate of the amount of dust coming into Mars' atmosphere, calibrating it from what we've done for the terrestrial atmosphere, and the fact that a significant fraction of this carbon is removed. And this would only make 0.05 ppb of methane in the atmosphere. Methane has a very long lifetime chemically in the atmosphere of 300 years or so. And so it should be very well mixed. And that's why there has to be a very small release at the surface in order to explain the observations of the NOMAD instrument on the trace gas orbiter, the TGO, which came up with an upper limit of 0.05 ppb, maybe even a bit lower now. So we feel that we are starting to close this conundrum here, which was, if all of this exogenous carbon was being deposited on Mars' surface, being irradiated in the UV, there should be a lot more methane in the atmosphere, which is not observed. And I think we have explained that. So let's conclude. The first important point is that we now think the total cosmic dust input into the Earth's atmosphere is 28 tons per day, most of it coming from comets, particularly Jupiter family, these short orbit period comets, rather than asteroids. Going to Mars, we were able to show, using a meteoric input function of magnesium based on or calibrated from the terrestrial input, that we can now explain the global layer of magnesium ions observed by the IEVS instrument on Maven. And the modeling with the PCM model, the global model, does seem to account for some of the unusual features. Not everything, but it seems to be doing quite well. I then showed you these lab experiments on the pyrolysis kinetics of organics in meteoritic particles. And now that we have actually measured the kinetics of this process when the particles reach well above 700 Kelvin, but particularly above 900 Kelvin, when things become fast relative to the rate of descent, that we can now work out what fraction of the exogenous carbon actually survives in particles. And this does seem to then produce an amount of methane in the atmosphere that is consistent with the latest measurements, but it's early days on that. So that's everything I wanted to cover. Thanks very much for listening, and happy to take questions.